I can't believe I did that. What a rookie move. So right away, if we start to read this, we say the following Wittig reaction, and you're like, Wittig? That's German. I pronounce it like a W. But in any case, we say Wittig, which means it's a named reaction. It's a named reaction, which means more than likely we're looking at something crazy and bizarre and what the hell's going on. Yeah, that's pretty much it. That's what's going on. Okay. So what we're going to try and process through is what's going on within the Wittig system. Okay. What we're seeing here beginning to end is the formation of the Wittig reagent. Okay. So if we look at that final structure, what reactivity do you see in that final structure? I know it's kind of small, but maybe you can pick it up. Say that again? Cool, a negative and a positive charge. Okay, which of those do you think is the more important one to talk about? A negative charge, because we've got a negative charge sitting on carbon. What did we just make? Carbon nucleophile. This carbon nucleophile can now go through and do all the crazy carbonyl chemistry that we were just referencing. But the question still comes about, how and why did this reagent come into existence? Because this is a lot of goofy stuff behind it. It's so goofy that we give it a name. I think I'm right. Could be wrong. No, I think I'm right. When we have this structure with the negative and the positive right next to each other, we refer to this as a yllid. So you might see reference to that. Okay? It's just something to be aware of. Okay? Officially, again, I'm not pushing you on names. If I'm going to give you a name, I'll give you the structure at the same time. Okay? Final exam, not written by me, you might see something different, but that's a goofy enough word, I don't think they would just throw that at you. I could be wrong. Okay? So, damn. What was the question that's being asked? It's to fill in the boxes, right? Yeah? Okay, cool. So we need to fill in the boxes behind this process to figure out how we're getting to this point. Okay, so that's a challenging question. So what we need to do is kind of think through this. Where do you want to start? C. Okay, why do you want to start at C? I agree with you, by the way.
Well, it's working backwards.
So why is C the best place to start when working backward? And cool. If we were starting with compound A, the only information we've got is what we're reacting with. So we might, if we were lucky, which you should be lucky, okay, and know what PBr3 does, you could predict what happens to the structure as going from A to B, but you wouldn't know about any of the hangers-on. You'd only know about that core kind of chemistry that happened within it. Okay? Why should you know? Just because I think you're making faces at me. Why should you know what PBr3 is for?
Oh, I saw PP.
There's a fair reason to laugh. Why should you know PBr3? This is actually from the last unit. This is unit 1.
Doesn't like fuck with the octet.
Unit 1 had all sorts of things going on within it. So there isn't like a nice thing like Unit 2. We can say, oh, it's carbonyl additions. Ta-da! Unit 1 is like, well, it's this and this and this and this and this. It's all over the map. Okay? So what part of Unit 1 did PBr3 fall under? It is in synthesis in the context of substitution. Okay? So what we're looking at is it's a substitution reagent. Okay? That reagent allows me to convert one functional group to another functional group that's useful in synthesis. Okay? Because the starting functional group has a whole bunch of chemistry associated with it, and if I don't limit that chemistry, it's hard for me to get it to do exactly what I want it to do. Okay? So do you happen to remember that? I was about to say, you two don't say anything. You clearly knew more about it than everybody else remembered, but that's okay. Nobody heard, right?
No, I don't pay attention to that.
No? Okay, cool. What functional group has a whole bunch of possibilities that could come out of it? So said another, we could say carboxylic acid. But carboxylic acids, what's the chemistry?
Acid?
Acid, so that's probably not what we're talking about.
Carboxylate?
Carboxylates are now the conjugate base of the acid and are now so stable that they typically don't react. That's why the conjugate, its partner acid, was acidic. But you could look at the carboxylate. Okay, again, resonance stabilization, but it's a negative charge. That could act as a nucleophile. It's not going to act as much else. So we draw that out with our negative charge. The negative charge could act as a nucleophile. We do have that polar pi bond, but that polar pi bond's not particularly reactive because resonance stabilization. So carboxylate, I would argue, isn't really a functional group. And that's an argument I would easily lose, so don't stress on that. Okay, but I would argue that's not a functional group, but that doesn't fit the category, because our category was we needed something with multiple chemistries. Do you know any other functional groups?
There's amine. Amine
Okay.
has a couple different ones.
Are you just trying to think of like all the shittiest, hardest ones?
Oh, yeah.
What a jerk. Okay, we could look at the amines. How would the amine particularly react? It's actually pretty straightforward now that I think about it. I had to draw it. It's acting as a nucleophile. It's not particularly, we could see it acting as a base, but it's still hinging on those electrons. It's not going to act as an acid because we'd form a negatively charged nitrogen, and that's not particularly stable. Okay, we could force it to do that by throwing in a strong enough base, but that's not high up on that. It's also not a great leaving group because it would be a negative nitrogen. Okay, what's the other option? Kind of its sister. I don't know which one of you said it, but we have an alcohol. What's special about alcohols? Well, they have the oxygen, lone pairs, which can act as a nucleophile and as a base. Yeah. Hydrogen is acidic, okay? And we have the potential for a nucleophile attack to do a backside attack on that, okay? The backside attack might be limited because
it has electrons there.
OH is a bad leaving group, but as we've seen in the lab, OH can act as a leaving group under certain circumstances. But alcohols are notoriously painful to work with as a functional group, or notoriously great, depending on your perspective, because they can do all the chemistries. Hooray! And if we're trying to do a particular thing, we may not want all of the chemistries. So what we could do is convert our functional group into something that has less chemistry. So there's our alcohol. The alcohol can react with PBr3 to turn the alcohol into a good leaving group, and then the bromine can come in and replace it, and we would get an alkyl halide. Why are alkyl halides better functional groups in that respect? It's about it. The bromine can act as a leaving group. Okay? So our chemistry gets vastly whittled down and narrowed within that field, and that's about all we get. Okay? If we were trying to draw an answer for this isn't going to work well for us, because if we tried to draw that and say, well, that's my answer, you're going to be wrong, because you're missing a bunch of other pieces, the rest of the hangers-on, if we will. Kind of make sense? Okay? But at least within that context, we know something about what those pieces are, and we can start to make predictions about this. Okay? Back to Ivan's original idea, which I think was an excellent one. Let's figure out what the heck compound C is. Okay. Compound C is arguably the easiest here because we know what the product looks like and we know what the reagent looks like. Okay. So, if we look at the product, what do we think was formed in the course of this reaction?
CH3 and CH2.
What?
Like there's 3 of the CH3 and the CH2, but only like 1.
Okay, so let's pause on that, because I don't disagree with that, but you're answering an entirely different question. I said when we look at the product, what do we think was formed? Okay, it could be a bond. What bond do you think is the most likely to form?
One that's connected to the reactants.
So when we say reactants, I'm saying, what bond is the most likely to form? And you're telling me to look at the reactions. I didn't ask about the reactions. I asked about that structure. What bond do you think is the most reactive? What's the most likely one to form?
I mean, couldn't a double bond be theoretically possible in this scenario, considering all the charges and negative charge?
Okay. So let's answer your question first. I have a negative and a positive next to each other. Could I theoretically draw a double bond? Yes. Is this a chemical reaction?
No.
What did you draw? Resonance. Why is that resonance special? That's one of the reasons why the Ylid comes into existence. Okay? This last reaction is allowed to happen not because I form a negative and a positive, but I get this potential resonance structure to stabilize the formation of that. So that's absolutely powerful. Again, not answering the question. We look at this structure and we said, okay, what bond? What bond was likely formed? And you might be struggling with that question.
A nonpolar bond? Is that what you're looking for?
Okay. Do you think you could make a nonpolar bond? Do you think that's the thing that makes this structure new and unique?
Probably not.
Okay. What do you think?
Well, I'm just going based off of the reactant but I don't know.
Okay. So fair enough. We could cheat a little bit. I think I need to backtrack out of that resonance form.
I don't understand.
And get
how
this back.
You didn't want us to look at the reactants one that would entirely tell us what bond is formed.
Not necessarily. Could this bond be the one that's formed? I would argue that's a half-decent bond to identify. Okay? Why is that bond a decent bond to be looking at? Cool. Let's shift focus. Why is the red bond a trash bond to be looking at?
Because it's nonpolar.
It's nonpolar. So if we look for that polarity, it can help to give us some clues about where the chemistry lies. Okay? And there's parts of the structure we can straight up ignore. And there's parts of the structure we need to be paying critical attention to. Okay? So if we're going to go through and say it's this green bond, I think that's the green bond that formed. If we go backwards through all of these reagents, what should we not expect to see?
Like green bond?
Maybe this PPH3, if that's my new bond, should show up here. In that step, because I'm saying that's the bond that formed, right? Does it show up there? No, it shows up even earlier than that, which means,
It's not.
that's not the bond that formed. So maybe when we look at this structure, we don't want to look for the bond, but again, what we're looking for is where's the chemistry within this that we could say, I think that's the thing that came out of this. So what's the chemistry of the Ylid?
What's the Ylid?
This structure.
Oh, the entirety of that? Oh,
Yeah. Officially, the Ylid is the negative next to the positive.
Oh, okay.
What's the chemistry of this molecule? The negative charge? Yeah, okay. Well, how could I make a negative charge on carbon? What would have to happen? I would have to break a bond. So if I went backwards to this compound C, that is way too small of a box. I'm not even going to try to do that. Okay. There could be a bond here connected to, I don't know, something. Okay. But in that something, what happens? The carbon takes the electrons.
Couldn't.
Okay? So what could I bond here that carbon would be willing to take the electrons?
Hydrogen.
Why hydrogen?
Because they're close in electronegativity.
Cool. We could look for that electronegativity difference. That electronegativity difference is a big tip-off that we could potentially be seeing that.
Does that act as a base? Oh, that'd be so fucked up. That better not be it.
Okay? All I wanted you to do was to think through what you had. Okay? Ivan had a lovely idea, and I chose to ignore him for a second. We'll come back to his idea here. Okay? We were given two pieces of information. I forced you to just look at one for the moment because I wanted you to think through what you saw there, think about the reactivity and how I could possibly get that. This is a possible result where the change that's happening here is that I'm removing that hydrogen. Okay? Does that mean that is what happened? The only way to figure that out is to also include the other piece, which means let's look at the other piece. But again, all we're going to look at is the other piece. I don't care what the final product is. I don't care what the starting material is that piece is reacting with. I want to know what that reagent can do. Where's its chemistry?
It will act as either a nucleophile or a base.
How do you know that?
Because the lithium's will be a spectator ion and will dissociate, leaving the negative charge to the carbon, I suppose.
Okay. So there was one statement that Ivan made earlier. We could go through and count the number of carbons, which is going to become even more important here in a second. Okay. But if we process out our structure, we have a bond between the lithium and the carbon. That's an ionic bond. As an ionic bond, we would know the electrons in that bond go to the more electronegative element. The more electronegative element in this case is carbon, which means I can ignore the lithium, and I now have a negative charge on that carbon.
Oh my God, it does that, doesn't it?
That carbon could now act as a base or a nucleophile.
Oh my God.
Both of those are potential options. Okay? Now we could start to factor in the other information that we went through and looked at with the yelid. When we factor that in, what happens? Okay? A couple things could come out of this. Number one, we said that, we put a hydrogen there, but we'd have to remove the hydrogen. What would we need to use to remove the hydrogen?
A base.
Does that align with the chemistry that we've already identified for that particular reagent? Oh my God, that looks pretty freaking promising. I like that idea a lot. But could have acted as a nucleophile. And if it acted as a nucleophile, it would have had to attach to the structure, right? Which means all of those carbons need to show up in your answer.
And yet, they don't.
Okay? I've got 1, 2, 3, 4 carbons, all sp3 carbons. Do I have 4 carbons sp3 in this answer? No. Okay? So Ivan, awesome that you saw that. Okay? If we look at the carbons, the pieces don't match. That eliminates the possibility of it acting as a nucleophile. Okay? Could Ivan alone on that first assumption, it can't act as a nucleophile, gone and said, well, it acts as a base. Yes, and if he said it acts as a base, then what does that mean the reagent had to act as?
An acid.
An acid. He knows the conjugate base because that's given. Now we have to replace the hydrogen. Both of those approaches take you to the exact same point.
I don't like that as a base.
Isn't that flippin' lovely? No matter what way you go, you end up with the correct answer. Boo, I don't like that. So guess what box 3 is? Box 3 is this guy. Sort of. I did miss something. What did I miss?
Charge.
Positive charge on that phosphorus. Absolutely right. It's not on the phenyl, it's on the phosphorus. Oh, and the phenyl. I get it. My bad. You're right. Okay. We'll put it in red so we can call attention to my failures.
Is it phenyl or phenol?
Is pH phenyl or phenol? Are they different?
That sounds like they might be.
Yeah, they're very, very different. Phenyl is a substituent. PHENYL. So a phenyl is a benzene ring connected to some kind of larger structure off that. Okay? So our structure would have to continue from that because it's a substituent. A phenol is the benzene ring, with an alcohol, an OH. Okay? It's not technically an alcohol. Why is it not an alcohol? You're like, dude, that question doesn't even make sense, Mike. Is this an alcohol? In red. I know, I'm doing it in red like it's my mistake. It's not my mistake this time.
suppose not. Question mark? Is it? I don't know, actually.
That's a functional group.
Yeah, that should be alcohol.
Well, no.
Is it still an alcohol?
No.
No, it's changed its chemistry because I brought two functional groups close to each other. What happened here? I took an alcohol and I connected it to the aromatic ring. Those are two separate functional groups. When I connect them near each other, there's the potential for them changing the chemistry. Did it change the chemistry? Yeah. That's why we call it a phenol, not a phenyl. And what moron came up with the name phenyl for all this is beyond me. Okay? Because, yes, that's stupid irritating. Okay? Not to be confused with benzyl, or actually even benzyl. YL versus IL is a whole nother system. But different can of worms, we don't need to worry about that yet. Maybe ever. Let's go with ever. Okay? So now we've got a new question. Right? We've got a new structure, box C. Okay? And because we remembered this stuff, how many people remember the stuff about the substitution? Ah, dang. Okay, that wasn't majority. It's all right, that all goes away. Right, we didn't know it. Can't use it. Okay? So we have this structure. Okay? We don't know what compound B is, but we know we're reacting a reagent. Okay? So we've got a couple pieces of information. We can run the exact same logic system. When we look at this new structure we've drawn, where's the chemistry? Ooh, the positive charge on that phenyl. Or that's not phenyl. Phosphorus. Okay? So that bond is now probably a high probability bond. And we'll change my hydrogen out. A high probability bond that I'm going to try and play around with and address that. Okay? How might I predict that bond to break?
Towards the phosphorus.
Why should we expect those electrons to go towards the phosphorus?
More electronegative.
Phosphorus being more electronegative than carbon, we would expect those electrons to go towards the phosphorus. So if all we're doing is thinking about this particular reagent, we might go backwards. I won't forget the phenyl this time. Maybe. We might go through and say something like that, where all we've done is taken those electrons. Except, what have I missed? Positive charge up on the carbon. Okay? This is a synthesis that can't be positively charged, but again, this gives us some of the pieces, the fundamentals that we could work with behind this. Okay? With that information, I could now say, okay, well, what does my reagent provide? My reagent provides PPH3. Okay? Oh, wait a second. I just drew that. I don't even have to think about PPH3 because I've already got it drawn, and if I thought about PPH3, it has a lone pair of electrons, which means it could act as...
The more you say it, the worse it gets.
I'll fix it. Yeah, you regret it.
You get a bond. I don't know.
It would act as a nucleophile. Right? It could act as a nucleophile with this thing. I already have the triphenylphosphine. Jerks. Right? Which means whatever compound B is must have some of this. But for this reaction to run, this has to act as a nucleophile. Okay? But it can't react with a positive. Something has to be there. So what would I connect to that positive charge?
Maybe a metal?
Okay? I like your answer the best. We had a couple different answers float out here, and 3 actually wildly different answers. Okay? A leaving group. The leaving group so that it takes the electrons with it so that our nucleophile could come in and attack. What things could act as leaving groups? Could it be a metal?
I mean, not technically a living group.
Yeah. Metals aren't leaving groups. What do metals do?
Float off into nothing.
They float off into nothing, leaving their electrons behind. So metal does not work as a good option for the leaving group. Okay? What was the other option? We could pick any of our halogens. Our halogens are phenomenal leaving groups. It focuses, really zeroes in on just that priority of the halogen leaving group. Okay? And we don't have a whole lot of else associated with it. So we could now go through and say, for this box, we just want a leaving group. Okay? And we could go through and say LG. LG isn't going to work. We have to specify the exact leaving group used.
Maybe bromide
Why would bromine be a good choice?
in the reactants.
the PBr3 supplies bromine. So as a general just blanket guess of any of the halogens we could have used, backtracking out to that reagent probably suggests that we're looking at the bromine. Okay? So we actually went past product B to figure out what our leaving group was so that we could backtrack into that. That works out okay. But now we have to come out with compound A. Compound A, we know bromine's a good leaving group. If we talk about its chemistry, the chemistry is in that bond. So we're talking about doing something associated with that bromine. If we're going through and saying that bromine is coming from our PBr3, we're saying we're running a substitution reaction, which means what needs to be connected at that position? A leaving group. A leaving group needs to be connected there so the bromine can replace it because we're going to run a substitution. The question becomes, what specific leaving group? There's tons of leaving groups that we could choose from. How do we know which specific one?
We don't.
You do. You have to know what PBr3 reacts with. So this now comes down very specifically to the reagent understanding of what PBr3 does in this particular reaction. PBr3 reacts with alcohols. In fact, it's actually different than that. It doesn't react with alcohols, it reacts with OHs. Any OH, and it converts the OH into bromine, which means that leaving group that we're starting with is an OH. We've now got our structures, our pieces, and we can put this all together into the individual system, and we should be able to get our
So it reacts exclusively with alcohol?
exclusively with OHs. I have to be clear with OHs because it will react with carboxylic acids as well.
Okay, gotcha. Does it react? That's the only thing it'll react with to do that?
PBr3, yeah.
Okay, gotcha.
Okay? Kind of, sort of. You get the process through all that. Okay. Last thing I'll kind of mention out there, was there another approach?
To go from the first to the last, I mean, technically.
So you could try and go from the first to the last, but again, you don't know what those hangers on are. That's going to be a hard approach to kind of nail down.
I didn't say it was a good approach, it's just another approach.
You could try and go to your textbook or the lecture slides and match out what each of those reagents are doing so that you can change the chemistry as you go along. We blanket just said, what things could we do? That's how we started this. This wasn't, it does this reaction, it does this reaction, it does this reaction. It was, well, what could happen? How do I think through and approach that to come to that answer? Okay? That approach is a valuable approach. What's the problem with that approach? That was 10 minutes per question. There were officially 3 questions there. You don't have time to do 10 minutes per question. Okay? That's ridiculous. Okay? So if you do this kind of approach, it's great. It's phenomenal. It'll help you process through reactions that you have not memorized. Okay? But on an exam, timelines, there are some things you will have to memorize. You have to decide what that is. I can't tell you. I can give you my opinions. I don't think the Wittig is one that I would memorize to get to this reagent because I feel with my practice, I can backtrack those reactions pretty quickly. If you spend the practice to get to that point, you can backtrack those reactions. That's not a big deal. There is a part of the Wittig that I do memorize, and we'll talk about that here in a second. But first, do we have questions about what's up there? Okay. What's the part that I remember with the Wittig? So, a couple things. First and foremost, I hear Wittig, and I immediately jump to the Ylid. Okay. That's a huge part of it. Okay, so I hear Wittig, and I immediately have that. Man, I'm going to have to redraw it over here. Okay, and we'll see why I'm doing this in a second. But this is what I see when I see Wittig. See the negative and the positive. Okay, why does that become important to me? Because what is the part that I've memorized as far as Wittig reagents? They're located in the carbonyl additions chapter. And what I've learned about my carbonyls is that my carbonyls via that resonance have a negative and a positive end. Which means if I'm now going to take my Wittig and react it with a carbonyl, what do I want to do? Align my negative and positive. So I'm going to take my carbonyl and drop my oxygen down here, my carbon up there. Okay? This now aligns those charges in the proper space. Okay? Here's the part that I memorize. I wish I had a neat. Well, there's not. This is as neat as you're going to get. I'll make it a little neater. The Wittig is a phenomenal nucleophile and fully swaps out the oxygen. What do I mean by fully swaps out the oxygen? Okay, well, if we were to sort of think through this mechanistically, negative to positive, this is going to create a four-membered ring. Four-membered rings stable?
No.
No, so what happens?
It immediately breaks.
It breaks. That looks like really ugly arrows, but let's process through it. What did the top two arrows mean? Call it arrow 1 and arrow 2.
Would act as a nucleophile?
Yeah? How many electrons did I move? 4. It's just like there's no way that's a real mechanism. It's not a real mechanism. This is the cheat. What happened with 3 and 4? How many electrons were moved? 4. Ta-da. Right. So what does the Wittig do? It converts the carbonyl into an alkene, and I'm connecting two larger carbon structures. Okay. Why is that powerful? Okay. If we think about just substitution, we're just swapping on one piece for another. That's it. That's pretty flippin' boring. Okay. When we talk about doing Legos, you don't just put one piece on and take it off. Like, that's a pretty silly Lego system. Nobody would buy that. Okay. What becomes cool is when you put one piece onto a larger piece and then you can stack and connect multiple things to each other. We just took carbon structures and we connected them to each other. We started with small carbon structures and now made it a larger carbon structure. That's powerful. Not only did we do that, we maintained some of the chemistry, because I still have now a pi bond, admittedly a non-polar pi bond, but I have a pi bond where I can continue to do reactions on the Wittig product. Right? So for me, what I focus on is just the formation, the alignment of those structures to go through and produce products. Okay. Is there a potential complication with forming alkenes?
They could react again.
They could potentially react again. Are they going to react again in the Wittig system?
Probably not, no.
No, because the Wittig system needed a polar pi bond. I don't have a polar pi bond, so it should be effectively fine as far as the Wittig solution goes. So they could potentially react again, but what I'm asking is about that alkene product. Is there something I should be concerned about?
Maybe resonance?
Resonance can come into play, but that's less of a concern. That's more about stability of this. We could be nice and redraw this. So clearly the phenol's up there. Clearly that's down there. Wait a second. What did I just draw? If you were to name this alkene for me, how would you name it? That's such a vague question. I hope you give me the answer I want you to give me.
Cringe.
Did you say French?
Cringe.
Cringe? Yeah.
It's like 3.
No, too hard. Think easier. Think the end of the naming process.
Heck.
What's the last step of your naming process?
Hex.
No, not the end of the name,
Oh,
the
what
end
the-
of the naming process. Hex is the beginning of the naming process.
Oh.
So,
The bond type?
Oh.
What do you mean?
So like it's the double bonds in there, so it'd be ene?
There we go. Okay. What we'd have to be addressing is cis and trans. Okay. When we run the Wittig reaction, we generate an alkene, and depending on the starting materials used, you have the potential for introducing a cis-trans isomerism, okay, or a cis-trans problem. Okay. Does the Wittig preference cis or trans? And it's a horrendously shitty answer. Yes.
It just.
Depending on your conditions and the structures bringing in resonance, you can see a preference for some Wittig reactions for the cis product. Switch up the conditions, and they favor trans. What are those conditions? We don't care. Okay? Which means all you have to show is that the formation of the double bond happens where it needs to happen. Whether it's cis or trans, as far as your drawing goes, doesn't matter. Okay? If both answers were provided, that's a typo. Okay? Because you're not responsible for being able to predict whether you get cis or trans. Because it's very nitpicky and detailed about how the individual hangers-on affect the overall reaction. That is way beyond what I want you to be able to do. Kind of make sense? Okay. So we're pulling out that there is a potential complication, but I'm trying to address that you do not need to worry about that complication. Why mention it at all? Because you'll eventually discover it as a potential complication. Okay, so I want you to be aware of it. Make sense? We also now have a cheat for it. Admittedly, that cheat looks pretty gross, but theoretically, as I was drawing it, it didn't look quite as bad. It looked bad all the whole time. Sorry. That's the only cheat I got for you. Okay? Next question. Unless there's questions about this.
I guess A, open exam, and see.
Is this exam 2? Is this right?
Yeah.
It's got to be right.
Isn't Nathan?
Oops.
This organic chemist also I'm good at spelling.
I'm telling your mom. That was recorded. 3 solvents are listed below. Describe what would happen, if anything, if each individual solvent was used for the following reaction. Right? So where should you start this?
Looking at what happens in the initial reaction.
Cool. So we're going to ignore the solvents. Let's just focus on what's actually happening in the overall reaction. So what happens in the overall reaction?
An addition.
Except, yeah, addition. Is it radical? For it to be radical, we need to be looking for a radical flag. The radical flag is either light, H nu, or roar. Neither of those appear there. So we're not looking at a radical reaction.
This would just split to a negative and a positive bromide, right?
Okay. So we could go through and look at the bromine. That bromine is likely to split where you're getting a partial positive on one end and a partial negative on the other. What's going to cause it to polarize?
The pi bond.
The pi bond. So the pi bond shares electrons inwards. I'm going to have to do it this way. It's a little frustrating, but that's okay.
And the negative would recombine with the positive charge on the opposite end of the pi bond.
And the negative would recombine with the opposite charge on the other end of the pi bond. Okay, that would suggest that this is happening simultaneously. The problem with this happening simultaneously is a couple things come out of this on why it doesn't work simultaneously. Number one, bromide, great leaving group. It is stable on its own. Because it's stable on its own, it's not going to immediately react right back. It's going to float off to solution and say, give me a second to breathe. I hate my twin. I wanted to live on my own for a little bit. Okay? So that's problematic. The other thing that's potentially more problematic is the sheer size of bromine, Br2, in comparison to the carbon-carbon double bond. So if we look at this, and I'm going to attempt to draw it to scale, but it's not to scale. We're looking at the carbon-carbon double bond, and if we now look at the bromine bond, why is the bromine bond so much larger? Two explanations.
I mean, it's connected to itself, so there's not much of a...
Carbon's connected to itself. I don't understand.
I mean, bromide is literally the biggest thing on there.
There's a lovely answer. Bromine is so flippin' large that when you bring those two bromines near each other, the overlap to form that sigma bond is going to happen significantly earlier than it is for the two carbons. Okay? So the size of that bond is now wicked large. Why has that become important? For us to form the bond with one bromine now pushes the other bromine so far away that it can't make that return connection. Why else would we expect the carbon-carbon double bond to be shorter than the bromine signal bond? That's the opposite answer that he just gave, same, opposite side of the same coin. Whatever that saying is. Thank you, Hans. Why else would I expect the carbon-carbon double bond to be shorter than the bromine-bromine single bond?
Well, you're kind of emphasizing the double versus single.
So why am I emphasizing that? Why would double make it shorter? There's an increased attraction between the carbons. What does that increased attraction do naturally?
Closer together.
Brings them closer together. Okay? So that carbon-carbon double bond is so short relative to the bromine bond that seeing it happen simultaneously, not likely. Okay? There are scenarios where it could happen simultaneously. Okay? Got lucky and that erased appropriately. When we move to hydrogen, why is hydrogen okay to happen simultaneously?
It's super duper small.
It's super smaller, so it sits pretty much effectively over those individual carbons. That allows for the electron transfer to all happen at the same time. Why else? If it happens stepwise, what happens?
You get a hydride.
You get hydride, which is incredibly unstable and doesn't want to come into existence. If we reference back our electrophile addition chapter, Mike's view on it, we're talking about the leaving group ability. If we have a bad leaving group, we're forming a four-membered or larger ring structure through either the transition state or intermediates. If we had a great leaving group, like our bromide, we end up forming the three-membered ring. So this reaction doesn't happen as two steps here. It's happening as one individual one, which sets us up with the phenyl, bromine positive, and our Br minus. Okay? This also becomes important because if we look at the hydrogen one, which I left there, since it happens at the same time, both those hydrogens are added to the same side of the pi bond. In the case of the bromine, because we get a hot second for the bromide to chill on its own, where does it come in and react? It comes in from the back side, and so it changes the stereochemical outcome. So if we're aware of that leaving group ability behind our electrophile, it can help us to frame what's happening with our intermediates, and it can help us to frame what the stereochemistry potentially comes out with our final products. That's why I think that system is a pretty neat system that I've invented, and I don't know why no one else has talked about that in the 100 years of OCHEM. Because finding those patterns, I think, is pretty cool. It's probably because I'm way wrong, but it works until someone proves me wrong, otherwise it will be fine. Okay? So we form this three-membered structure. The bromide could now come in and attack. What's the bromide acting as? A nucleophile. Since it's chilling on its own and doesn't really feel the need to react, could we potentially have added a different nucleophile?
100%.
Yeah. In fact, when we look at the reagents, Br2, one of the other reagents we could do is Br2 and H2O. So that we add a bromine at one position, and then we would add OH at the other. Because now water being present in the solution outcompetes the bromide for that nucleophile attack. Right? So if we're thinking about the solvent, what is the solvent supposed to do in this reaction?
It's supposed to dictate if the bromide gets there or whatever is the other substituent of the other side.
I'm going to work with that and say that what you're saying is the solvent is supposed to dissolve those species and make sure those species are independently stable on their own so that the
I'll
reaction can
pretend
happen.
like that's what I meant or said.
Yes, good. Okay. What is it not supposed to do?
React.
React. Okay. And if we consider the overall reaction, the big thing that we're concerned about is this bromide needs to come in as a nucleophile. So what should the solvent not do?
Act as a nucleophile.
What makes a nucleophile?
Electron.
A source of electrons. So now that we understand what we're looking at within the details of that mechanism, we can now answer the question about what solvents would be potentially hazardous for this individual system. And if we go through and look at CH3OH, what does CH3OH supply?
OH.
It supplies the oxygen, and that oxygen could act as a nucleophile. And in fact, it aggressively does, and it would do the same thing water would do, and it would replace that bromine with a CH3. Okay? Is that a really hard question to go through and process?
No.
Okay, that's not how I saw it, but that's fine. Okay. Okay, I think that's pretty hard. You have to process all those individual pieces to be able to answer the overall question. Okay? A version of this question showed up on an old ACS question, okay, where they were asking about this in a slightly different format. I think they asked Br2 and then they used CH3OH as the solvent. And students invariably put just Br2 on. And they ignored the solvent OCH3. Why? Because they never saw CH3OH as a solvent. So they just assumed it was a solvent, didn't worry about it. They didn't also memorize that H2O could have been used instead, and that CH3OH is really just H2O with an extra hanger. Right? So if you can look to those pieces, you can start to pick out those potential pitfalls and traps that get thrown in. Okay? If we move to NH3, NH3 is also a really good nucleophile, and as we talked about in this particular unit, okay, our lecture videos, I believe, for last week, nitrogen is a phenomenal nucleophile and one that is so good that we can't really control its nucleophilic characteristics, which means we don't use it, okay, because it's just obnoxious. What about CCl4?
I mean, not altogether, but couldn't the chlorine act as a leaving group and then be a nucleophile?
Okay. Which is now getting back to the overall character behind this. Because this is a question that several of you have multiple times now gone through and said, well, chlorine's got electrons, so it can act as a nucleophile. Can it? If it acts as a nucleophile, it is now sharing those electrons with another structure. Say again?
Doesn't want more than one bond.
It doesn't want more than one bond. If it doesn't want more than one bond, that's not going to happen. Just because there's electrons does not make them nucleophilic. You have to process where those electrons are located and their abilities to potentially run those reactions. Which means carbon tetrachloride is just a solvent. It does nothing else. Those halogens won't do much of anything. To the ability of it acting as a leaving group, there are systems where you could try to manifest this and force this to happen. It's not a pleasant reaction. And it is a variation of one that we've looked at. You're forming a carbocation. The negative chloride now could theoretically go through it and react. This carbocation isn't super stable on its own. Why not? What are the chlorines doing?
Taking electrons.
They're taking electrons away, making the carbon
More positive.
even more positive. So that carbocation is actually not particularly stabilized and is very, very reactive. Right? And the modified version that we looked at in the electrophile addition, it was similar to diazomethane. You're using it to form carbenes. Carbenes are a super reactive secondary class. Usually result in the loss of fingers.
Couldn't you also argue this pure?
Just a second. I'm going to stop the video for the moment because we are past class time.